we're going to be showing some of our end-to-end testing and data we've collected through these different techniques. So hopefully you'll get something out of seeing these different end-to-end tests. And then finally, bringing this all together and suggesting what this could mean for us clinically when we use SGRT practically. All right, so there's many different factors, as I'm sure you're all aware, that contribute to the accuracy of an SGRT system. Kind of core to all of that is a good calibration. So good quality calibration data defining the optics of the system are kind of key. Without this, it doesn't matter what else we do with our ROIs, with our skin tone selection, all that. Nothing would matter if the calibration is not as good as it can be. So whether or not you know it, for those of you that use Align RT right now, there's really two key areas of calibration. The first one is the extrinsic calibration. So right now, if you're using the large calibration plate, you're doing your monthly calibration. When you're positioning that at 100 SSD, you're basically defining your extrinsic calibration. So where are your camera pods relative to each other, and where is your isocenter position for Align RT? If you have the SRS license and you use the MV isocenter calibration cube module, then you're going to fine-tune your isocenter position to make it more accurate to your treatment isocenter. The second type of calibration is your intrinsic calibration. So this is basically calibrating anything within the pods, so the optical parameters, so our focal length, our distortion correction parameters, for example. And we do this right now with our large plate again, still during monthly calibration. When we raise the plate 7.5 centimeters, at this position here, we're calibrating the intrinsic properties. So I'm going to be describing new techniques for both of these types of calibrations and presenting some of the data we've collected for this. So starting with extrinsic. So this is how well we define our isocenter for Align RT. So the first question is, how does this impact us? Why are we really interested in improving accuracy for the isocenter location? And there's really kind of two key areas I think that are important here. Whenever we set up a patient against their DICOM surface, if there's an offset between the Align RT isocenter and the treatment isocenter, it doesn't matter how well you align the patient initially, they'll always be offset by that same amount that your isocenter's offset. I think more importantly, though, is what happens when we rotate the patient's surface, when we rotate the patient during treatment. And I just want to illustrate the impact of an offsetting calibration. So this diagram here shows a patient they've been set up to IGRT. We've had a reference surface captured. I'm depicting here in red is our treatment isocenter, and in yellow we have where we've calibrated the Align RT isocenter to. So we're just illustrating here an offset between the two, so if it hasn't been calibrated perfectly. So we go ahead, our treatment plan has a couch rotation, we rotate the patient rotates perfectly in this example around treatment isocenter. We then rotate our surface, but our surface, Align RT, only knows where the isocenter is based on how we calibrated it. It uses the information of this yellow isocenter point, so it rotates around the yellow isocenter. You can clearly see here there's a discrepancy where Align RT expects us to be versus where the patient actually is, and the patient's in the correct place. We're going to get some real-time delta values as a discrepancy between the two. So just to kind of illustrate this with a little figure, let's say we have a millimeter offset between the Align RT isocenter and the true treatment isocenter. So let's say we just use our large plate to calibrate, and when we initially set that up for monthly calibration, it was offset by a millimeter. Well, when we rotate the patient, assuming there's no couch walkout and patient motion, as we rotate towards plus or minus 90-degree rotation, this offset in isocenters is going to lead to a 1.5 plus millimeter mag walkout. So this is going to happen every single time. Any of you out there that treat with rotations and you routinely see increasing real-time delta values as you rotate, chances are it could be because your calibration is slightly offset for your isocenter. So even if we have an offset of only 0.4 millimeters, we can still get, as we rotate the couch, up to about 0.6 millimeter walkout every single time we rotate the couch. This is a systematic offset. It's going to be inherent due to this offset calibration. And if we have a millimeter threshold for our SRS treatments, for example, this is a significant chunk of that. So we want to eliminate this, and the goal is to basically have no offset. So how do we do this? So our goal is to get the best isocenter calibration we have, to get the best coincidence. So we ran through some tests, basically running through the typical isocenter calibration procedure. We perform monthly calibration with the plate, and then you see on this right-hand side, we have kind of an in-house made bespoke rotating platform. The idea is we can position our phantom on top of this platform and rotate this very accurately around its isocenter. So using this, we eliminate any couch walkout potential. So we're just looking at the accuracy of a line RT in this case. So we perform MV isocenter calibration on this phantom, and then at 15-degree increments, we rotate the phantom and see how well a line RT can track this phantom for these known positions. So there's two things we're testing here with respect to the MV isocenter calibration procedure. The first one is kind of the more traditional workflow for MV isocal, where basically while we're acquiring MV images to co-calibrate the two systems, we can potentially have continuous monitoring. So we're continually monitoring the surface of the cube during this procedure. We recently sent out a customer information bulletin about this procedure. Due to some work we've been running, we found a new improved workflow for MV isocal. And if you haven't received that CIB yet, I believe we have some copies and we can talk about this later. But the basic idea with this new workflow is that during the MV isocal procedure, we're not going to monitor the cube after initial setup, and then immediately before running the radiographic analysis of our images, we're going to capture a new surface, so we get the location of the cube via surface imaging at that last step. So let's look at the data we collected. So first of all, for these rotations with method 1, where we're continually monitoring the position of the cube throughout MV isocal, you can see that as we rotate the phantom on the platen, we can see that the real-time delta values increase. Even though we've done the best we can to calibrate this, we've applied all the shifts that MV isocal suggests, we're still getting this real-time delta walkout. And from the plot previously, in theory, this accounts for about a 0.4 millimeter offset in our calibration accuracy. So obviously 0.4 millimeters is pretty small still, but every time we rotate this phantom or conceivably the patient on the couch, we're going to get this increase in real-time deltas that's not truly reflecting the position of the phantom. The second method using this new CIB workflow is the data is presented here in blue. Essentially, as we rotate the phantom, we get no walkout of the real-time deltas. So at plus or minus 90-degree rotation, there's no change in the real-time deltas for tracking that phantom versus where we believe the phantom is or where we know the phantom is. So it's kind of the bottom line here is that with this new workflow, we've essentially been able to eliminate this isocenter offset from the calibration. And I think hopefully I've shown that this is important when you're treating with couch rotations in particular. You want to make sure you have the best coincidence of those two isocenters. So again, if you haven't seen this new workflow, I would suggest pick up a copy on your way out and talk to me about it as well. We can discuss that. But I think this is key, and like I mentioned before, if you are rotating the couch and you're seeing routinely more walkout with the real-time deltas than your couch walkout should suggest, then the chances are you have an offset. All right, this is the new bit. So everyone scoot to the edge of their seats a little bit. So this is with respect to the intrinsic calibration. So this is defining the optics of the camera. So I mentioned right now we do the raised plate calibration, and we basically capture the focal length and the different parameters from each sensor at that one location. So our goal is to take a look and see, is there any way we can improve the tracking accuracy with a line RT, looking at a wide range of clinical configurations. So within SGRT in general, there's some more challenging configurations. So for example, when we're treating with couch rotations, when the gantry is blocking one of the pods, when we have a very deep isocenter, that's a challenging configuration for SGRT. So we were looking, and over the past several years, we've been working on a solution such that it doesn't matter what configuration you're in, it has limited impact on our tracking accuracy. So we're pleased to kind of introduce here advanced camera optimization, so ACO. So what is ACO? It's a new calibration technique that replaces the existing raised plate portion of monthly calibration. So this is a service run activity. So we have trained service engineers that will come in. They have their own dedicated ACO calibration plate. And the idea is that they're going to calibrate the system over about a 30-minute procedure with the calibration plate at lots of different positions throughout the field of view. So rather than just capturing calibration information at one position, they're going to be capturing optical information at a variety of different positions and angles. So what does this give us? This gives us better information for the camera sensors over a volume as opposed to just a plane. So if you imagine our surface, depending on isocenter depth and location, our surface is going to move around within the field of view for different patients. Well, the idea with this is if we have a better 3D model of the camera optics, we should get a better, more stable accuracy. So that's the hypothesis with this, and I'll show you some data in a minute. Because the internal optics of the cameras are extremely stable, this is intended to be a single one-time event initially for setup, and then there'll be kind of ongoing spot checks to make sure that the accuracy is still there, and if there's any degradation for whatever reason, we can repeat that procedure. So how do we test this? Basically following some guidelines from TG 147 and some different in-house testing, we set up a series of 3 different tests, as you can see here. The first one is absolute setup accuracy. So this is basically taking the phantom and running through a typical workflow as if it was a patient. So going from the CT process, the planning, and to setting up the patient using surface guidance. And we're seeing how well we can set up this patient compared to internal CBCT imaging. The next step is how well can we track the phantom under known shifts under relatively straightforward conditions. So with no couch kicks and no gantry rotations, how well can we track a known displacement of the phantom? And then finally, probably the most challenging case is taking a look and saying, right, let's stress this system completely. Let's give it different couch kicks, different gantry angles, and different isocenter locations and see what effect this has on our tracking ability, again, in phantoms. So I'm going to run through these tests and show the data that we've collected so far. And incidentally, we have about 14 initial rollout clinical sites using this, so most of this data was collected from those centers. And we're also getting feedback from clinical usage as well. So I'll discuss that in a moment. So firstly, the absolute setup localization assessment. So this is our basically patient treatment workflow. So we take our phantom. In this case, we use 2 different phantoms. We use the SRS cube that we use for MV IsoCal, and we use the Max HD phantom. I know we've discussed elsewhere in this meeting. It's an anthropomorphic head phantom we can see out back. And the idea is we CT the phantom with a relatively small slice thickness, and then create our treatment plan, create our DICOM surface, and import this as a patient into a line RT. We then, just like we would a patient, we set up the phantom using just a line RT. We zero out the deltas, get it as close as we can, and then we acquire our CBCT to confirm how accurate our setup was. And the results were, for the Max HD phantom, the absolute setup, we were able to position this phantom to within 0.2 millimeters of the CBCT conformation and 0.4 degrees. So that's units of millimeters. So that's, I think, extremely tight. For the cube, which is a slightly more straightforward phantom shape, we could get it within 0.2 millimeters, 0.2 degree accuracy. And just a point to note, actually, I've put a diagram up here, a screenshot. When we run these tests, and if anyone wants to replicate these kind of tests, we recommend, or at least I recommend, positioning the cube at a 45-degree angle for this workflow. A couple of reasons. Firstly, in CT, we don't want any faces of the cube parallel to the slices. We get better resolution if we're rotated, so we're not parallel to the slices. And also in the treatment room, when we're using surface guidance to view the cube, if the cube's rotated to 45 degrees, our lateral cameras can actually see 2 of those vertical faces each, versus if it's at the 0 position. So I think just a little tip there. So we've tested how well we can set up the phantom. Now we need to take a look and see how accurately we can track known shifts of the phantom. So the next test is our coplanar known shift test. Again, kind of following loosely at least the TG 147 recommendations. So one problem we found with this test is that it turns out a line RT is probably more accurate than any other mechanical system in the LINAC environment. At least it stresses those other systems. So to run this test, we had to devise a new mechanism for accurately moving the phantom. So we used a motion stage like this, and calipers and different calibrated scales to be able to accurately measure the displacement of the phantom. So the idea is we position our cube again at a 45-degree angle, And then we shift the cube plus or minus 1 and 2 centimeters in the different translational directions. And then using line RT, we measure the actual real-time deltas against the known position of the cube. So I'm showing here in this figure, it's a little hard to see, I'm just showing one of them. This is just for longitudinal shifts. So in green, when we have 0 displacement, plus 1 centimeter and plus or minus 2 centimeter shifts vertically, longitudinally, sorry. All of our real-time delta values were within less than 0.15 millimeters of the known phantom position. So for this phantom study, these known shifts in this coplanar setup, we could track this phantom within less than 0.15 millimeters. So again, I think quite impressive. The next most challenging test is looking at this kind of non-coplanar, kind of full end-to-end test, mimicking the typical workflows, the typical configurations you'll see during SRS treatments. So the idea here is, again, we use our rotating platform so that we can eliminate any potential couch walkout as a variable. So at the 0 position, we capture a reference surface of our max HD phantom. We then go through a variety of different setups. We rotate the platen plus or minus 45 degrees, plus or minus 90 degrees to mimic couch rotation. And then for each of those positions, we move the gantry, so it's either at the 0 position or plus or minus 30 degrees. And what that does is, at each of those 30-degree increments, we're going to block one of the lateral camera pods. So at that time, we're just using 2 cameras, basically, to view the surface of the phantom. Not only did we run through these tests for one isocenter, but we looked at the effect of different isocenter depths on the surface tracking ability. We had a question in the physics session earlier about the location of the lesion and its dependence on surface tracking accuracy. So we're sensitive to the fact that it could have an impact, so we wanted to test that here. So some of the data from this. Firstly, looking at all the data pulled together. I've split it out by rotation of the phantom here. But basically, the worst case we saw, so the largest real-time delta relative to the known position of the phantom using ACO was less than 0.4 millimeters discrepancy. So this includes the extremely deep offset isocenter, couch kick to 90 degrees, gantry blocking one of the pods. We still were confident, or we knew the position of the phantom to less than 0.4 millimeter accuracy and less than 0.2 degrees. So what impact does isocenter depth have? So the hypothesis I kind of gave earlier was because ACO calibrates the optics over a volume, we should be able to move around within that volume and get comparable accuracy for our surface tracking. So we looked at different isocenter depths ranging from shallow at 3 centimeters down to deep at about 16 centimeters, and included some offsets as well. And you can see the difference plotted here. This is the average real-time deltas we saw. But from the shallow to the very deep group, there was only 1/10 of a millimeter difference in the tracking, the maximum real-time delta values we saw. So extremely stable. And then similarly, what happens when we block one of the pods? Again, because we have a more accurate calibration model of the different pods, the idea is if we lose information from one, the other two, the accuracy of the calibration of those should have enough information and be robust enough to not cause a big difference in the real-time deltas. That's exactly what we saw. We saw less than 1/10 of a millimeter change when we rotated the gantry to block one of the pods using ACO. So what does this mean for all of us? Well, first of all, I believe that this could benefit all treatments. We've looked at sub-millimeter accuracy, and one question could be, well, I'm just treating breast, why do I care about 0.2 millimeter accuracy? An additional benefit, which I haven't really shown the data here, but is just the stability. The better the optical model we have from our cameras, the more accurate or more robust the surface is that we're creating. So if you're doing a matching algorithm with a very robust, stable surface, the chances are you're going to have much more stable real-time delta values. There's going to be less fluctuations. So I think that's a benefit. I mentioned we had 14 sites that are using ACO currently, and just kind of picking up on some of the feedback from these centers, kind of replicating in patients what we've measured in the phantom data, reduced pod occlusion effects. So they see less of a jump with the deltas now when they block the pods when they're treating their patients. The real-time deltas are more stable. I think a really significant bit of feedback is that in real patient data for SRS treatments, certain centers have been able to replicate the effect we've seen, where if you go to a deep isocenter treatment, it doesn't affect the tracking accuracy versus the shallow isocenters. So it's always good to get the confirmation in real patient data to mimic what we see in the phantoms. And then, because we're calibrating over a volume, we have better tracking accuracy at distances further away from isocenter. So if you have an extended SSD treatment or an extended SSD setup for whatever reason, again, we've had feedback that surface guidance with Line-RT and ACO is actually more accurate now. One area I like to highlight with respect to these kind of accuracy levels is when we're treating single isocenter SRS treatments with multiple METs. So as we know, under these situations, if you have a distant MET away from isocenter, we're very sensitive to patient rotation in particular, where if the patient rotates a small amount, you get that kind of lever arm effect, where a small rotation at a large distance could lead to a relatively large motion far away. So under this case, it's extremely important we know where the patient is throughout treatment. And I think these kind of techniques are becoming much more popular. We discussed HyperArc earlier. I think that's a great application for this type of treatment, and just more conventional LINAC-based opportunities for this as well. So I think there's a real need to kind of drive towards the best accuracy we can get. I think the data we've seen from ACO is a great step forward, and I think could add a lot of value in the clinic. So just to kind of summarize what we've talked about, so in its current format, we have sub-millimeter accuracy with a Line-RT. However, we're always looking, as I've trying to demonstrate here, at opportunities to enhance this further and to get more reliable, kind of robust feedback from the real-time deltas. The first approach, using that new MV isocenter calibration workflow, will hopefully reduce, if not eliminate, the calibration offset with isocenter to make treating at couch rotations much more robust, so we don't see that systematic walkout effect. And secondly, with ACO, a lot of hard work and a dedicated research team has gone into creating this ACO procedure, calibration technique. And I think the ability to track a phantom with the data we've seen with less than 0.4 millimeter accuracy is pretty impressive. And I think it's a great outcome for the hard work they've put in. Just the very bottom line, calibration is essential. If you have a poor system calibration, it doesn't matter how good your ROI is, it doesn't matter anything else. You have to have a good calibration. But once you have that good calibration, we still have to pay a lot of attention, as we know, to other workflow-related issues, such as carefully selecting a good region of interest, good skin tone selection, things like that. So I haven't talked about that here today, but we still obviously have to make sure that we get the full package for the treatment to get the best accuracy that we can. So with that, I thank you for your time.